So without further ado, let's get into our first session. Starting off this day is a session on planetary defense, DART's Bullseye and other missions. And again, sponsoring all of our sessions today is Northrop Grumman, so thank you to you all for your support. Our moderator for this session is Tarek Daly. Tarek is a senior professional staff here at JHU APL. He was deputy instrument scientist for the Draco camera that flew on DART and is part of the small body mapping tool development team. He has a PhD in Earth, Environmental, and Planetary Studies from Brown University, among other degrees. Welcome to Tarek and the panel.
Thank you so much. So this last February marked the 10th anniversary of the Chelyabinsk bolide. This was a tiny asteroid that exploded over the atmosphere near Chelyabinsk, Russia, and caused a blast wave that struck 6 cities around the area. It caused injuries rather, to more than 1,600 people and an estimated $30 million in damage. If we look back in the geologic record, we know that other asteroids, much larger asteroids, have collided with the Earth with graver consequences. But we are not helpless against this celestial onslaught. In recent years, we have had significant advances in planetary defense, some of which we'll hear about today. This includes the release of a national near-Earth object strategy and action plan, the inclusion of planetary defense for the first time in the decadal survey that came out last year, the successful demonstration of kinetic impactor technology for planetary defense, and the confirmation of a NASA mission designed specifically to find near-Earth objects before they find us. To tell us more about the past, present, and future of planetary defense, I'm joined today by our panel. We have Lindley Johnson, Nancy Chabot, Paul Abel, and Amy Meinzer. Lindley Johnson is assigned to NASA Headquarters, Science Mission Directorate, Planetary Science Division, as the NASA Planetary Defense Officer and Lead Program Executive for the Planetary Defense Coordination Office, tasked with warning and response to any potential impact of Earth by an asteroid or comet. Prior to NASA, he served 23 years of Air Force active duty, obtained the rank of Lieutenant Colonel, and was awarded numerous military honors and decorations while working on a variety of national security space systems. Nancy Chabot is a planetary scientist at the Johns Hopkins University Applied Physics Laboratory. Her scientific research focuses on understanding the formation and evolution of rocky planetary bodies in the solar system. She is the coordination lead on NASA's Double Asteroid Redirection Test, or DART mission, and has also served in a variety of community leadership positions, including chair of the NASA Small Bodies Assessment Group and chair of the panel on small bodies for the recent National Academy's Planetary Science and Decadal Survey. Paul Abel is the chief scientist for small body exploration within the Astromaterials Research and Exploration Science Division at NASA Johnson Space Center. His main areas of interest are the physical characterization, robotic and human exploration, and research potential of near-Earth objects. He is an investigation team member of both NASA's Double Asteroid Redirection Test and NEO Surveyor planetary defense missions, as well as a science management board member of ESA's Hera planetary defense mission. Finally, Dr. Amy Meinzer is professor at the University of Arizona, whose research focuses on understanding the populations of small bodies in the solar system, including the characterization of potential impact hazards they may pose to Earth. She is the principal investigator of NASA's Near-Earth Object Wide Field Infrared Survey Explorer mission and survey director for NASA's NEO Surveyor mission, which will carry out a comprehensive survey for the most potentially hazardous NEOs and is scheduled to launch later this decade. Lindley, Nancy, Paul, Amy, thank you so much for being with us today. The rest of the panel will unfold as follows. Each of our panelists will give a brief presentation of some highlights of planetary defense from their respective perspectives. We'll then have a few questions that I'll share with the panel before opening it to all of you to share your questions. Lindley, I believe you're first. Please take it away.
Okay, thank you very much, Tarek. My job here is to kind of set the stage for the rest of the panel and talk about overview of the planetary defense program at NASA. And this is a very touchy device. Okay, here we go.
That's why you're first.
So the PDCO was established now 7 years ago at NASA headquarters under the Science Mission Directorate, Planetary Science Division. Because planetary defense is applied planetary science. We are able to do what we do because of what we've learned about these small bodies in the solar system that come close to the Earth over time. And so we're tasked with organizing and supporting the efforts to, first of all, find any potential impact hazard to the Earth and be able to assess whether it's going to be a significant event, cause damage at the surface, or it's just going to be one of those bright lights shows in the sky that we're able to see every night as a meteor or a meteoroid. And then if there is a serious threat, to have worked the technologies and the strategies that could be used to respond to that. Hopefully we have found it far enough ahead of time in space, that's our objective, to be able to do an in-space deflection, like we demonstrated the technology with DART, or if not, if timing is short, have the information to be able to tell our leadership and the emergency response community what we might have to deal with. This is the framework on which we hang the entire planetary defense program at NASA. It is we call our sector chart, and it shows all the different areas that we're involved in planetary defense at NASA. Read it clockwise, so starting up at the upper right, the most important thing we do is find them. We have to find them first. We can't do anything about them unless we find them. And so a good amount of our effort is focused in that area, surveying the skies, finding this population of near-Earth objects, asteroids, and comets that over time their orbits bring them into Earth's vicinity. Then we have to understand something about that population, both in general, what their nature is, but if a object of interest or a potential impact threat is found, be able to find out as fast as we can what we are dealing with, the size, mass, composition of that object. Then, not so much funding-wise, but certainly involved in a lot of our time at PDCO is planning and coordinating with both the within the U.S. government, the U.S. interagency, and with our international partners around the world on what our response might be should a threat be found. Working international collaborations, some of which you're going to hear about here today, and also the planning and coordination that would have to go up at national and international levels. Then the sector that all the Hollywood movies about is mitigation. What do we try to do about the object while it's still in space? And that's what DART was all about, testing a technique with the technology we have available to deflect in space, but also in this area is if we have to take the hit on the ground because of late warning or whatever circumstances, preparing with the FEMA and the emergency response community on that. And finally, we have to be able to assess our success in doing all these activities. So our current assets that are surveying the sky every night possible are shown here in this world map. Most recently, we've added several Southern Hemisphere assets now with the 2 additional Atlas telescopes in South Africa and Chile, and also working with the U.S. Space Force, Royal Australian Air Force, with the new Space Surveillance Telescope in Australia. We also have one space asset that we use, NEOWISE, repurposing of the Astrophysics WISE spacecraft from 12 years ago now, and now dedicated to asteroid hunting, and a prototype for the NEO-Surveyor spacecraft. Our tasking from the U.S. Congress is to find this population of hazardous asteroids, currently threshold 140 meters and larger, that could do significant damage were they to impact of a 140-meter size object is enough energy that could devastate a statewide area. So that's kind of why that threshold is set. It represents kind of an existential threat to national security. Currently, we've only, based upon our population analysis, only found about 42%, and so we have a ways to go there. So that is why we are embarking on things like the NEO-Surveyor project to find them all, and so we know where everything is and what could represent a threat. So you're going to hear about the enhancement and capability that's going to provide us. And then on the mitigation side, the DART demonstration, which I know you've heard about, but Nancy's going to tell you even more about it.
Great, thank you so much, Lindley. And there's really no way that you can give a DART presentation these days without starting on September 26th of 2022, the day that humanity first deflected an asteroid. This was watched by more than 1 million people concurrently as NASA broadcast here from APL, where the Mission Operations Center was, the final moments of the DART spacecraft, Mission Operations Center down there in the bottom left. Finally, the asteroid that had never been seen before coming into the field of view. Celebrations everywhere. This had been years of effort across APL, across the country, across the world, this idea, this concept of taking this first step for planetary defense. The DART camera working until the very last minute, sending just that little sliver of the final image until it met its fate into the asteroid. It was an amazing accomplishment, an amazing team that made this happen, and rightfully celebrated. I want to sort of also point out here, this was all done autonomously. Everything that you saw there, the spacecraft had to autonomously navigate itself to a small asteroid that had never been seen before. And that autonomous navigation system turned on when it had this view, 4 hours out. And you cannot distinguish the asteroid Dimorphos, which is the one it hit, from Didymos, the larger one that it orbits about. Instead, it's just a single point of light, and this is when the autonomous navigation developed over many years kicked in. Dimorphos was finally detected 73 minutes prior, and at 50 minutes prior, with this view from the spacecraft, it started to target not towards Didymos, but toward Dimorphos, firing its thrusters autonomously to ensure that center head-on impact. This was a huge challenge. It was a major accomplishment, and targeting a small object in space about which you have limited information when it's millions of miles away from the Earth is obviously a highly relevant capability for planetary defense. But while we were celebrating that accomplishment, rightfully so, because it was a huge accomplishment, LiCiaCube was working. So the Light Italian CubeSat for imaging of asteroids was a CubeSat contributed by the Italian Space Agency. It rode along with DART and was deployed 15 days in advance. And then it made its close flyby 3 minutes after DART's impact. And it stored those images on board, so we didn't get them the night of impact, but it played them back the days and weeks that followed. And what you're seeing here is a movie of those put together. It's approaching the asteroids. It actually turns around and looks at them as it flies on by on its way out from the other side. Just very clear, beautiful debris ejecta coming up from Dimorphos because of DART's impact. Spectacular images. That shows you the wealth of the data set, but I feel like you also need to look at each image individually to just appreciate the detail and the complexity and the morphology here. This is a single LiCiaCube image that's stretched a factor of 2 with each box, so you can bring out that fine detail of the rays and the filaments and the debris that was thrown out through DART's impact. Still a lot of work going on to fully understand this and model it. That's about where the team is doing right now. Not just LiCiaCube, telescopes around the world and in space. In fact, telescopes on all 7 continents at this point have contributed to the DART's team investigation. And I really just want to stress this international cooperation for the international issue that planetary defense has really enabled us to maximize what we've learned from this unique first test for planetary defense. I'm going to show just a few snapshots because there are dozens of telescopes that are contributing and have spectacular data. The telescopes in Africa were the ones that were positioned to look up at the night sky and capture DART's impact event. And here you see one example from the Atlas telescope that Lindley talked about a second ago. Just very clear, obvious evidence of material and debris and vapor coming off during DART's impact event. Multiple facilities captured this view. While we were celebrating, while LichioCube was working, these were also shared on social media. So immediately while people were celebrating, they were seeing this in their feeds. Again, this worldwide effort and collaboration in order to advance planetary defense. Here's a view from a telescope in Chile that was taken 2 days later, where you can see the initial ejecta, but you also see this really long tail beginning to develop. 12 days later, this is a nice shot from Hubble Space Telescope showing the complex evolution of that tail. It had a double tail briefly, which turned out to be short-lived. And just jumping ahead, because I could show you a lot, but it's 64 days post-impact from New Mexico, Magdalena Ridge. In this field of view here, this is about 30,000 kilometers. We estimate at least 1 million kilograms of material in that tail that you're seeing coming off. And this is just a few weeks ago, because observations actually are ongoing until the end of March. Hubble has the opportunity and is continuing to take observations until July even. So 143 days post-impact. This is from Arizona, Lowell Discovery Telescope. The tail is fainter, Didymos is getting further from the Earth, but the tail is also actually getting fainter as is there, but it's still clearly there. Watching this full evolution of the ejecta, we're learning a lot from the DART impact.
Notice the other asteroid that photobombed that image.
That's a great example of it, isn't it? You should see the full frame. There's more asteroids. Actually, we have a little test to people figure out what that is. If you can figure out which that other asteroid is, we'll give you a bonus something. Yeah, I mean, but these are going on, and they've been so incredible, just this collaboration. And as much as spectacular as the ejecta is in the images, one of the main things the telescopes had to do was tell us how much the asteroid was deflected, because DART did not do that. It just crashed. It did not tell you how much it moved that. LichioCube did not either. It just flew on by, spectacular images, but we needed to rely on the telescopes here on the Earth to make that crucial measurement. And these are the same telescopes that had discovered this system, the Didymos-Dimorphos system, and they had looked at it for decades. And they knew, like clockwork, Dimorphos goes around Didymos every 11 hours and 55 minutes. This has been measured in extreme precision, which is why this was a great object to then do the DART test for. So DART came in at 6.1 kilometers per second, and LichioCube was kicked off 15 days in advance. DART slams into Dimorphos, like we saw. LichioCube captures spectacular images. And that slamming of the spacecraft into Dimorphos changed the trajectory of Dimorphos around Didymos ever so slightly. How much? And that's where the telescope made that measurement, and it turns out that the orbital period was changed by 33 minutes. Now, if just the momentum of the DART spacecraft had impacted into Dimorphos, and that's the only momentum transfer you got, you would have changed it by about 7 minutes. So 33 minutes is much bigger than 7 minutes, which shows you that you're getting an enhanced deflection because of this ejecta, because of this recoil effect. This makes this a very promising result for potentially applying this technique in the future, that you're really getting this enhanced, efficient deflection from this simple kinetic impactor idea of deflecting asteroids. I also, though, want to point out that it is a spectacular result for this 33-minute change, but it's also less than a 5% change, right? The whole point behind kinetic impactor deflection is to do it many years in advance. A small nudge doesn't really change the asteroid that much, but you do it many years in advance, and that time lets it adds up to a bigger change in position with time. And so something like DART needs to work as part of a larger planetary defense strategy, like Lindley was showing. You need to know where the asteroids are, have the warning time, and then something like this is very promising potentially if the need should arise. And I just kind of want to end with this image, because we can talk about DART as this pioneering mission that's accomplished a lot for planetary defense, and all of that is absolutely true. But I know a lot of us here at APL, especially where the spacecraft was built, still think of it this way. It's a very human-sized spacecraft that was sent on a mission to move an asteroid. And that was done by many people over many years, coming up with the concept, building a spacecraft during COVID, launching it, operating it, and now still continuing to analyze the data to really fully understand. A great example of what we can all do working together to advance planetary defense. It's been an honor to be part of this team. It's a very, very large team, and just to be here today to share it with you. And I'll pass over to Paul, because DART is just the start, and there's more to
Small
come.
but mighty spacecraft.
Thank you, Nancy. So good morning, everyone. I'm representing the international component of the Hera mission that ESA is going to launch. So one thing I'd like to tell you is that DART and Hera are part of AIDA, right? The Asteroid Impact and Deflection Assessment. DART did the asteroid impact. We have some idea of what happened, but we really need Hera to go in with its CubeSats, shown there on the slide, to really find out what happened, what did we do to Dimorphos, what happened at the system, and what we actually did. How effective was the impact? We know it was very effective, but what was the actual momentum enhancement? So we need to know key things about Dimorphos itself, the mass particularly. And did we form a crater? Did we deform the asteroid? How big was the crater if there was one there? So those types of questions we're going to do. So a little bit about the Hera mission. Planned launch is in October of 2024. Arrival in late December of 2026. And this is a bit of an eye chart, but you can see sort of the mission timeline here. The entire mission is supposed to last about 6 months to 1 year, with detailed operations, close proximity operations at the Didymos system. So you start off with a rendezvous phase as you approach, looking at the system in its entirety, doing some basic hazard assessment, going in slowly, figuring out what's what. Then there's going to be a early characterization phase, get a bit closer to the system, to the asteroids in general, figure out how you're going to plan for the detailed operations that will happen in a few months' time. Then there's the deployment of the CubeSats. There's 2 CubeSats that are deployed, so it's a very exciting mission operation perspective. These CubeSats are very capable and will help with the detailed characterization phase later on. And then ultimately there's a close operation phase where you get really up close and personal with the objects, trying to understand what that crater's like, if it's there, trying to understand what the structure and mass of Dimorphos, trying to understand what even Didymos is like. One of the exciting things is we're planning is trying to actually land on the asteroids with multiple spacecraft. So this is something that we call the experimental phase. It's to the end of mission, but it's something that we'll hope to get a lot of information that also is very important for planetary defense, but also very important about understanding asteroids in general, and particularly binary asteroids. 1/6 of all the near-Earth objects in our population are estimated to be binary objects. So this is something that is very important, not only for science, but planetary defense. So this is, Hera's the first mission to rendezvous with a binary asteroid. It's also going to visit the smallest asteroid up close and personal, Dimorphos, with about 150 meters. It's going to be the first investigation of a full-scale cratering experiment. We can do this in lab, obviously, but this is going to be the first time that we've got all the information we need to understand what we actually did with DART. Also, it's going to be a technology demonstration mission because we're going to use CubeSats to investigate an asteroid up close and personal in deep space. And that's going to be very exciting. Also, we're going to get a hint on what the internal structure is like on Dimorphos. We have a radar on one of the CubeSats, so we're going to actually be doing some radar tomography. A little bit about the Hera spacecraft itself. Again, launch is October 8th, 2024. Really busy time this year, as you can imagine. So a lot of integration, a lot of testing is going on. The highlight of that will come a little towards the end of 2023 and the better part of 2024. But activities are really ramping up. People are really busy on the team. A lot of testing is going to be done at STEC and ESA all the way through 2023 and 2024, up until the delivery of the spacecraft to the Cape for launch on a Falcon 9. A little bit about the mass. As Nancy said, DART was human size. This is a little bit bigger than human size, so it's about twice the size of DART. Appreciable amount of power. Basically, 13 meters in cross section with the solar panels deployed, and we had 18 countries, European partners, who contributed instruments, and also we had an instrument contributed from Japan. Here is the payload suite on Hera. There's a core payload and the CubeSats. So the main core payload consists of asteroid framing cameras. These are both for science and navigation. We have the Japanese thermal infrared camera there, the imager. We also have, obviously, the radio science, which will help us a lot, not only with communication, but also the radio science experiment. We have a laser altimeter, which will help with science and navigation as well. And then there's a multispectral imager in visible wavelength range to help determine the composition. And then, of course, we have the two CubeSats, Milani on the left, so it has an imager, multispectral imager, retroreflectors, a dust analyzer, also helps out with radio science. And then Juventus, which has the radar experiment, gravimeter, and also radio science. So Hera mission is really going to be really important for understanding what we did, right? It's going to be getting at the crux of what we actually did at Dimorphos, what our first test of this demonstration, and it's going to help us understand binary asteroids. So it's very important for planetary defense and science. And that, I will leave it to Amy.
Great. Thanks a lot, Paul. Well, so I'll talk a little bit here about the Near-Earth Object Surveyor mission. So the brilliant success of DART demonstrates that we actually can do something about this, which is really pretty amazing. I mean, that, like you said, it's a human-sized spacecraft and you can actually do something about it. Our job is to supply you with targets. So basically, the Near-Earth Object Surveyor mission's fundamental objective is to find the objects well in advance, so that hopefully the simplest possible technique, the kinetic impactor technique, can be undertaken, because we really do think that that's a very effective way of moving things out of the way. But we have to supply them with the targets and good quality orbits, as well as some very basic physical characterization information, so that we can understand which targets are really worth paying attention to. So the objective of this mission, you can see a picture of it here, is really simply to find the objects well in advance, and find the objects in particular that are large enough to cause ground damage that's appreciable. The Earth is, of course, impacted with small objects all the time. Most of them are absolutely harmless, but it really does boil down to getting a pretty good estimate of the size of the object, because the kinetic energy scales as the size cubed. So our objective is to find the objects, including objects that are optically very dark. We know that the near-Earth object population consists of a group of roughly brighter, stony class objects, a few metallic objects mixed in, but also a non-negligible population of objects that are very carbon-rich and are extremely dark on their surfaces. So by searching with infrared light, as opposed to visible light, we're now more or less equally sensitive to the population of bright and dark objects. And we can also get a pretty good estimate of the sizes just from the infrared measurements alone. So that's really the objective of this project, is to find the objects, figure out which ones are worth worrying about. We're going to do this using a fairly modest-sized telescope. The primary is about 50 centimeters, and we'll have two channels that will span sort of the peak of the thermal emission curve for most of the near-Earth objects that get pretty close to the Earth and the Sun. So operating between 4 and 5 microns and about 6 and 10 microns. And that's enough for us to kind of scoop up the thermal photons from these asteroids, as well as get a fairly good measurement of their effective temperatures, which in turn helps us to constrain the diameters. Now, because this is a thermal infrared telescope, we have to keep the instrument cold, as well as the detectors. In other words, we don't want to be blinded by our own thermal emission. So to that end, we need to put the telescope in an environment where it is cold. Now, the existing telescope that Lindley mentioned that I also work on, called NEOWISE, is currently in Earth orbit. It's a low Earth orbit. and it is equilibrated to about 75 Kelvin. Long after its cryogen was exhausted, after the successful completion of its prime mission, which was cryogenically cooled, we're achieving temperatures of about 75 Kelvin in low Earth orbit at about 450 kilometers. That's a little too warm for us for NEO Surveyor, so we need to get a little further away from the Earth. Our chosen environment is the Sun-Earth L1 Lagrange point, which provides us with a couple of advantages. It's cold, so it's easy for us to actually passively cool the observatory by just keeping that tall sunshade that you see there pointed at the sun, shielding the instrument. And then we just basically paint the back surface of it with a very efficient radiative black paint. And that will be enough to get us to the cold, stable temperatures that we need to operate our instrument and detectors. The other advantage of this environment, of course, is that it's close enough that we can get all of our data back. We do carry some pretty large detector format, or large format detector arrays, so that we can efficiently map the sky. And to do that, we want the highest possible data rate we can get. So L1 is nice because it's close and it's consistent in terms of its distance to Earth and the data rate. We were confirmed to go into phase C on November 29th of last year. So we're off to the races now. So that's really fun. And it's an exciting time. Like Paul was saying, this is when the rubber really hits the road. So we're really happy to be at this point. And we're looking forward to our launch, which is in September of 2027. And so the mission is slated to operate for 5 years. We perform an extremely repetitive survey. In a lot of ways, we have sort of the DART's operations are so exciting and ours are super boring if we do it right. We're just going to do the same thing over and over and over again for 5 years, really just tiling the sky, looking and mapping carefully. So we're sort of the nerds of the planetary defense world in some ways. But if we do it right, we should be able to quickly and efficiently map out the sky here. So I'm showing you now sort of a top-down, if you will, or bottom-up view of the solar system with the sun at the center. And you can see the two cones of our visibility windows, which Lindley introduced in his earlier charts. The survey progress goes pretty fast, and we should be able to fairly quickly rack up a large number of objects within our 5-year baseline. So the level 1 requirement is to find 2/3 of all the potentially hazardous asteroids larger than this 140-meter size limit within the 5 years. And if we keep going, we have a reasonably good chance of meeting the congressional objective of getting to 90% after about a decade or so. So in event, we will find hopefully the next set of interesting targets for Nancy and her crew to push aside, and for Paul and his folks that he works with to examine. So that's it from me. Thank you.
Thank you, panelists. So to get us started here, the first question is, there aren't any more near-Earth objects now than there used to be. We just know about more of them and we know more about them. But progress towards addressing this threat has changed a lot in recent years. From the panelists' perspective, what has helped accelerate that change recently, where we're having greater action in planetary defense than we were having in years past? Lindley, perhaps you want to start with that one?
Well, getting hit by something always brings attention. The Chelyabinsk event back in 2013, I think, spurred a lot more action because, that was something that everybody got to see via the dashcam videos that was all collected. And although NASA, under congressional direction, had been hunting for this near-Earth asteroid population since 1998. First of all, the large kilometer-size objects, but then threshold 140 meters. But that event, really then spurred the interest and the realization that the threat is still out there. It's just a matter of time before we do get hit by something significant.
Other thoughts?
Well, it is kind of a tough problem for people to think about, in the sense that, these are long-term problems. And we tend as a species, I think, not to respond to something unless it's right up in our face. So this event, I think, really did catalyze people to take it more seriously and think about what we could do. And it turns out we can do something about it, which is great. I mean, how many natural disasters can we, for a fairly reasonable program size, actually say that we can solve it or largely solve it?
Nancy or Paul, other thoughts?
I'll just say that I think this is something that resonates really well with the general public. You know, this is something that's on their mind. I think there was a recent study that suggested the two major things that NASA should concentrate on was climate change and planetary defense. And I think that's one of the reasons why we were starting to see this uptick. I mean, obviously getting hit in Chelyabinsk, that certainly helped gather attention, but this is something that's been on the general public's mind, and this you know, the DART mission totally resonates with the general public. They get it, and they understand how important this is for future generations.
Yeah, and I mean, I guess I'll maybe just add and not call anybody out in particular, but I mean, constant advocacy, you know, for this issue. I mean, Lindley deserves a lot of credit here, right? I mean, how much has this program grown at NASA? There wasn't a Planetary Defense Coordination Office until 2016. Other people in this audience has also been very important for making these advances happen in ways, right? So, I mean, along with the progress, finding the kilometer-sized objects, the incident of Chelyabinsk, I think, you know, it's not enough. You have to also constantly be advocating.
And certainly there have been examples of that through the Small Bodies Assessment Group and various National Academies reports as well.
A couple of bad Hollywood movies where the science is really horrific.
I don't know, the core is pretty bad and we haven't been there yet, so.
We'll do one more question from me before we open it up to all of you. But as we look forward, say, you know, 10 or 15 years in the future, what do we think planetary defense will look like? And maybe Amy, start with this one in the context of advanced surveys.
Well, one of my hopes, I would say, is that we learn a lot of wonderful, interesting science. We find new destinations to visit. We find new places to go and study, but I'm hopeful that we don't find anything that looks actually truly hazardous. That would be the best possible outcome from my perspective, is that we do a very thorough search and we find that, you know, there maybe are some close approaches, but there's really truly nothing out there that is hazardous. That would be the best case. You know, but hope is not a management strategy, right? So in the event that that's wrong, I think it's very good that we have demonstrated deflection techniques of various types and also rapid characterization, the ability to quickly go and find out more than we can learn from our remote observations about the physical properties and you know, the size, the shape, the spin state, porosity, internal structure. Those are all parameters that you really do need to know if you're going to seriously attempt to deflect something and be very confident that it's going to work. So with any luck, in 15 years, we will have completed a very thorough search. We'll understand what is out there. We'll have identified anything that looks bad or interesting, I guess, depending on your definition. And that we'll have also been able to take DART a step further to the next parts of characterization, to the next parts of understanding how to deflect an object. So that, from my perspective, would be success.
Absolutely. In 15 years from now, if we haven't found all the 140-meter size objects that are out there, then that's going to be a huge disappointment. But the Earth has been hit by objects for billions of years, and this will continue, right? I mean, and national policy sort of puts the mark at 50 meters, right? And there's a lot of those out there. And so DART was an amazing demonstration of a technology demonstration mission, right? We are a long way from an operational capability. Part of, and working on the decadal survey with Paul as well, I really hope that from here we have a regular cadence of planetary defense missions going forward, right? Part of DART's success, I think I will judge personally by it being the start, by this being the first thing, NEO Surveyor following after that, and other steps to put us on this path towards this future that we want to live in, where we can protect the Earth, can give ourselves warning time. And that's what I want to see. There's a lot of different steps that can be taken, but as long as we're further down that road and have this regular cadence of doing these space-based missions to advance planetary defense, I think I think we're on track to do that too. I'm very optimistic with the success of DART, with Hera going to launch, and NEO Surveyor finally going to find the asteroids, because we can't do anything about them if we don't know where they are.
And I would agree. I mean, one of the things being on lots of asteroid missions is we're constantly surprised by what we see when we get there. This is every mission that I've been on, there's always been a surprise. And one thing for planetary defense is you don't want to be surprised. So having an understanding of what's out there, making sure we have this cadence of missions for planetary defense, I think is really, really important. An ongoing type of program to demonstrate and refine our capabilities to react just in case we come up with something. One of our famous colleagues has said, and Nancy knows this is sort of my mantra, she's laughing now, she knows what I'm going to say, she knows exactly what I'm going to say, is we don't get to choose the asteroid. The asteroid chooses us, right? So now we did DART, and that was a great demonstration, but we chose that specifically for that purpose, right? And that's one data point. It's the start, as Nancy said, but we really got to be ready for anything that comes our way.
I don't think I have anything to add to all that, so let's take some questions from the audience.
Yes, absolutely. So we'll go for the two microphones, and we'll check online and go back and forth. So first question over here.
Rather than solely reflecting asteroids, do you see DART expanding so that it would attach to an asteroid to better characterize the asteroid and understand what resources it's bringing from outside of our current solar system and understand the flight speed of the asteroid and just better characterize its flight path?
With anything that would be a threat to the Earth, I think as much information as possible ahead of time would be absolutely desired. And I think that's why it's so important to be characterizing them, finding them, gaining that information, right? To put yourself in that position. I think also, though, you want to plan for potentially the worst case scenario, which is a limited amount of time, a limited amount of information, right? If you can deal with that, then you can deal with this other one where maybe you could rendezvous with it, maybe you could do other things with there. So I think it's again, I don't want to speculate too much because I think there's a lot of steps to go forward from here. Maybe we'll let NASA speculate because, he is the planetary defense officer for the entire country. So, I'll let Lindley take it from there. But I mean, I think sometimes the warning time is really the key to put everybody in the best situation to have the outcome that you want.
Sure. I mean, our whole strategy is to have the maximum warning time that we could have. So that's why we're doing NeoSurveyor. NeoSurveyor is designed to find anything significant that's out there that could be an impact threat for at least the next 100 years or so. And it's that advanced warning time that gives us the best options, a wider set of options of more benign options that could be used to then deal with it in space, and we're not have to worry about it here on Earth at all.
Hi, this is Charlie Steckmiller. So congratulations on your technology demonstrator. Could you characterize what you learned about the impact and what the materials itself was made out of? Because it's not a Psyche type of solid body, which would be a totally different response than the one you got.
Yeah, so one of the things that the telescopes have found, right, before when you looked at the Didymos system with ground-based telescopes, it just looked like a single point of light in the optical telescopes. But when DART crashed into Dimorphos, it put a huge amount of material up, as you saw there from the LiCiACube images, and the telescopes also looked at that, and they were able to get the spectral information for the first time about Dimorphos. And we know now that it is an ordinary chondrite type material, an S-type asteroid, which is perfect for planetary defense because that's the most common type of material to hit the Earth. So it's not like Psyche, which is a metal-rich body out there. Just in such a fortunate position that Hera is going to get there in late 2026 and follow up in 2027. And I'll let Paul talk here.
Yeah, and I mean, that's one of the key things that Hera is going to do, right? Investigate the system in entirety, figure out what it was made of, what's the internal structure like, is there any differences in terms of the surface and at depth? It looks like Dimorphos may be a rubble pile, but what is the actual porosity? Is there more solid chunks, larger chunks underneath that near surface layer that we saw with DART, but we didn't have a chance to actually investigate in detail. So that's what Hera is going to do. Hopefully,
so
answer
seeing
all
that
those questions.
impact crater or the disturbance of the surface will then tie back to the simulations that are being done now, right? Which will be kind of for different strength materials and really give us this whole other insight. It's still one data point. Right? I mean, at the end of the day, right? So, I think, it's great we're taking this first step, but there's a lot to learn about these small asteroids. And, Amy, I don't know if you want to chime in. I mean, some of them are dark. They have different compositions, they're not all the same.
Yep, that's right. I mean, there's a wide diversity of object types and materials, and they all have different structural properties. That's another thing. The prevalence of rubble piles, I think, is something that's very interesting to work on, because that's a structure that we don't really see on Earth in the terrestrial meteorite collection. It just doesn't survive passage through the Earth's atmosphere that well. So yeah, we've got a lot to learn still.
Any questions online?
We have one question actually related, talking just about the energy transfer that may have happened with DART. What have you seen? What does that tell you for future implications?
Yeah, so what we're finding is it's not just what you brought in with the DART spacecraft that we're getting for transferring for deflecting this asteroid, but actually considerably more than that. In fact, a significant, more than just what the DART spacecraft brought in is the ejecta that's kicked off the surface, giving you that extra push, giving you that extra recoil effect. We just published a paper actually in Nature last Wednesday, so there's got a bunch of details and numbers in there. Tarek was one of the lead authors of some of the papers that goes through some of the specifics of the mass and the speeds and things like that. So really happy to have those out in public at this point.
This will be for Nancy and Paul. So basically, Nancy, you know from Messenger that some of the largest impact basins had an antipodal effect, or diametrically opposite, where the shock wave comes together. But on this object, given how small it is, how irregular it is, probably a lot less dense than Mercury, I would guess that that would not be in play. Any comments on whether any small amount of ejecta was observed on the opposite side from the impact, and whether Hera will be looking for that?
Yeah, I mean, Jim, you would be fascinated by the models that our impact working group comes up with. Trust me, they destroy the whole object sometimes. They don't really. It's still there. We see it. Radar detected it. That was
Anyway,
a
is
joke.
this anything
But
to
yeah,
this?
I mean, these low gravity rubble pile objects are very counterintuitive. Because they are small. They are not like Mercury, like like you said for Messenger. And you can get all sorts of things that happen there. That said, the DART spacecraft was about the size of the golf cart, and it crashed into something about the size of the Great Pyramid, right? So you still do have this scale factor. It's a very impressive result. There's a lot of ejecta, but it still is only a less than 5% change in the orbital period, right? I mean, so in that sort of sense, I think some people had some lofty models that maybe you would see something on the other side. That said, there's a lot of ejecta in that system, right? A lot of it left, but some of it's going to fall back down in various places. And what Hera finds is going to tell us interesting things about that. It's also great to expose material that used to be at depth on any object. That gives you new insights into it. And we're very excited because Hera isn't just flying by, it's going to stay there with this great suite of instruments to get this information.
Yeah, I mean, we're going to try and look and see exactly what happened, not only on Dimorphos, but also Didymos, right? A lot of the material that was released, undoubtedly some of that actually interacted and hit Didymos, right? So what did that do to the Didymos, the primary, which is roughly around 800 meters, a little shy of 800 meters? What did it do to that object? Did it change any of the dynamics of the system? Those are the type of things that Hera is going to be looking for. So yeah, we'll see.
Next question over here.
Yes, my question is, given the Lichia cube and the Hera hosted CubeSats, what is the discussion and what are the plans for future hosted payloads, to support these missions, and possibly even, with the MMX rover on the Phobos exploration move, and maybe even deploying micro rovers in addition to CubeSats?
I'll just say really quickly that Lichia Cube performed spectacularly. There were challenges, absolutely, as you get with developing any CubeSat. They worked them out, and I think, the proof is there in those images. And so I think, that's a real milestone for CubeSats operating in deep space and what they have the potential to cover. I don't make policy, so that's exactly where my heart stops, but I don't know who wants to pick it up.
Well, certainly, Lichia Cube exceeded expectations, and we're very happy with the results of that. I think it's going to be a common thing that future exploration spacecraft are going to carry their.
Going to be what can happen. We've already seen the success of deployables on Hayabusa 2, for example. and how the deployable camera observed the small carrier impactor experiment on Rugu. So I think this is a way, like Lindsay said, I think this is going to be a wave of the future for having small deployable spacecraft or assets that will help augment the mission.
And okay, next question, and perhaps the last question because of time. Okay, let's see.
Have there been any models developed so far based on the DART data that scale up to if Dimorphos were the mass of Earth and we had a 140-meter asteroid, how many impactors we would need to send and what mass those would need to be approximately?
So for the decadal survey, we sort of have a plot in there, which is, asteroid size versus like warning time. And, there's techniques other than kinetic impactor that if you're in the unfortunate situation of a large object with short warning time, which we're not going to be in because the new surveyor hopefully is why, so it's so important. You need to do other techniques potentially, right? So I think it's again, like DART's one part of this mitigation strategy. I think Lindley said a few times, like having multiple tools in your toolbox, might be the way to go. So I'm going to pass to him to fill that part in there.
Yeah, that's definitely part of our strategy is that we will test other technologies and techniques as well, so that we have a full toolbox available. And we see that what we're going to be faced with is very scenario dependent. It depends on the warning time, of course, but also the size and the orbit of the asteroid as to what might be the most effective way to deal with it. The strength of the asteroid, again, you can only hit it so hard with one impactor. Maybe you can do multiple impactors, but if you have enough time, there are other more softer techniques, more benign techniques that could be used.
Final question.
I'm Myra Montrose. Congratulations on DART. I'm so happy about Near Surveyor getting confirmed. My question is more futuristic and policy-wise. Lindley, you have the coolest title, like definitely in this room and probably in the world. Do you envision how are all the countries going to coordinate such an activity? Because this is not a US kind of thing. And it's really cool that we have all the land-based telescopes, the ground-based telescopes to help out. But do you see, how do you plan that collaboration as we take this planetary defense further into helping?
Yeah, well, in regards to the title, when I was about age 35, I realized I was going to never be an astronaut. So I had to come up with something that gave me at least the coolest title as that.
Well, congratulations.
So that's pretty cool.
Achievement unlocked.
But international collaboration, I probably didn't stress enough how big a component that is of our overall planetary defense program and effort. Through negotiations with underneath the United Nations Committee on Peaceful Uses of Outer Space, the Scientific and Technical Subcommittee, the Coalition of the Willing, I will call them. There are many countries that are involved with us in this endeavor. And the European Space Agency is one of the strongest partners, but also space agencies around the world. There are two entities. First of all, the International Asteroid Warning Network, which is an operational network composed of over 50 signatories around the world who are contributing their capabilities and techniques to finding this population. Everybody sends their data into the Minor Planet Center. And also characterizing these objects and understanding their nature. So there's already a strong international collaboration going on to find and warn of them. The other entity is the Space Mission Planning and Advisory Group. This is
For the